If the universe ever wished to speak to us, it would not choose words or light or the quiet drift of galaxies. It would choose a black hole. Nothing else in existence compresses so much truth into so little space. For all our telescopes and equations, humanity still understands less than a fraction of 1% of what a black hole truly is. We name them as if they were simple pits in space. Yet they are sculptors that bend the very fabric of space-time until geometry loses, meaning Ton 618 and Phoenix A sit at the far ends of this extreme cosmic architecture. They are not just massive objects, but milestones that tell us how violently and how beautifully the universe evolves. Around them swirl the great unanswered questions of physics. The firewall paradox that challenges the nature of the horizon, the no-hair theorem that insists black holes cannot hold memories, the information paradox that refuses to die despite decades of debate. Each paradox is a reminder that our laws crack open the moment we approach the event horizon. Something fundamental shifts there. Time twists, space recoils, certainty collapses. And as we stand before these cosmic abysses, one whisper rises from the darkness. To understand the universe, you must look toward the place where light gives up. To understand a black hole is to study the most extreme architecture the universe has ever built. A structure governed not by intuition, but by the raw geometry of general relativity. Its first and most deceptive feature is the event horizon, a boundary where the mathematical fabric of space-time reshapes itself. Outside this boundary, time behaves like time and space behaves like space. Just beneath it, the roles invert. Time-like paths become space-like, and every possible future collapses into a single direction that leads inward. Nothing escapes because escape is no longer a meaningful word in that geometry. Hidden deeper still lies the singularity, often described as a point of infinite density. Yet many physicists argue it may not be a physical point at all, but a region where our mathematics has simply reached its limit. The singularity might be a wall of ignorance rather than a physical object, a sign that quantum gravity has not yet spoken its piece. Surrounding this invisible core is the accretion disk and the corona, a pair of structures that radiate more power than any star we have ever observed. Gas spirals inward, heats to billions of degrees, and lights up the cosmos in X-rays and ultraviolet fire. This luminous violence turns a silent black hole into the brightest beacon in the universe. In rotating black holes, the story becomes even stranger. The spin drags space-time into a whirlpool called the ergosphere. Inside this region, nothing can remain still because space itself is being pulled around by the rotation. This dragging effect allows energy extraction through the Penrose process. A mechanism so exotic it borders on science fiction, yet is fully permitted by Einstein's equations. And towering over all these features are the relativistic jets. Narrow columns of plasma launched at more than 99.99% the speed of light. They carve through intergalactic space, imprinting the black hole's signature onto regions millions of light years away. The deeper we explore this anatomy, the clearer it becomes that these are not merely objects. They are gravitational organisms sculpting the universe with every heartbeat. But this is only the part we understand. The rest lies in shadows. TON 618 is not merely a black hole. It is an eruption of gravitational power so vast that even numbers struggle to contain it. With an estimated mass of nearly 66 billion times that of the Sun, inferred from accretion luminosity models rather than direct dynamical measurement. TON 618 exists in a regime where normal astrophysics begins to tremble. Its quasar blaze is bright enough to outshine hundreds of Milky Way-sized galaxies combined. Astronomers do not just observe it. They witness a lighthouse from the early universe burning at a distance so great that its light began traveling long before Earth even formed. Its origin likely traces back to the epoch of reionization, a time when the first stars and galaxies ignited and reshaped the cosmic fog left after the Big Bang. For TON 618 to reach its present mass, its seed must have been extraordinary. Either a direct collapsed black hole formed from a primordial gas cloud, or an exotic relic born from the universe's earliest density fluctuations. Whatever it was, it grew in a way that violates the quiet assumptions of cosmic evolution. Its accretion rate appears to surpass the classical Eddington limit, implying bursts of super Eddington feeding that challenge the stability models of radiation pressure and disk turbulence. This abnormal growth suggests either a hidden supply channel of cold gas or physics that our simulations do not yet include. The reach of its gravitational influence radiates across millions of light years, sculpting its surroundings, heating intergalactic gas, and leaving a signature that spans epochs. TON 618 is not a monster because it is large. It is a monster because it should not exist with the scale it has, and yet it does. And in that defiance lies a message from the universe. TON 618 is only the beginning of the darkness. Phoenix A sits at the heart of the Phoenix cluster, a gravitational metropolis so dense that galaxies orbit it like sparks caught in a cosmic furnace. At the center of this furnace lies a black hole whose mass may approach 100 billion times the mass of the Sun, according to some extreme upper bound estimates. If TON 618 is a cosmic beacon, then Phoenix A is a devouring engine, a presence that feeds not on a single galaxy, but on an entire cluster wrapped around it. What makes Phoenix A extraordinary is not only its size, but the environment that sustains it. The Phoenix cluster is home to one of the most powerful cooling flows ever observed in the universe. Hot intracluster gas radiates energy and cools, losing pressure support and cascading toward the core in a continuous inward river. This cooling flow delivers a near inexhaustible supply of fuel to the central black hole. Gas that would take billions of years to settle in other clusters rains down upon Phoenix A with staggering efficiency. The result is a feedback loop so violent that it transforms the surrounding medium. As Phoenix A feeds, it releases energy at a rate comparable to tens of thousands of supernovae every second. Jets and shock fronts carve cavities through the intergalactic plasma, hollowing out vast bubbles that reveal the raw mechanical power of a supermassive black hole in full force. These cavities are not scars. They are signatures, fossil imprints of eruptions, so intense that they reshape the thermodynamics of an entire cluster. This makes Phoenix A a natural laboratory for high regime physics, a place where relativistic plasma, magnetic turbulence, and deep gravitational wells interact in conditions that cannot be reproduced anywhere else in the cosmos. Here. The universe tests the limits of its own laws. If Ton 618 is the lantern of the darkness, Phoenix A is its forge. Ton 618 and Phoenix A represent two opposite poles of cosmic evolution. Two archetypes forged by entirely different regimes of astrophysical power. Ton 618 shines as a quasar beacon, a radiant wound in the darkness that broadcasts energy across billions of light years. Its luminosity is not merely brightness, but a declaration of unrestrained radiative accretion. Gas spirals inward at extraordinary rates, heats to incandescent extremes, and releases torrents of electromagnetic light. In the early universe, such quasars acted as cosmic lighthouses that illuminated the primordial fog and marked the birth of large-scale structure. Phoenix A, in contrast, hides beneath the dense shroud of its cluster environment. It is a buried black hole whose brilliance is not measured in photons, but in mechanical violence. Instead of glowing as a quasar, it exerts power through jets, shocks, and colossal feedback cycles that excavate cavities in the intergalactic medium. Where Ton 618 shines, Phoenix A reshapes. Their divergence reflects two evolutionary modes that sit at the heart of black hole physics. Radiative mode growth, exemplified by Ton 618, thrives on luminous accretion, where energy escapes as light. Mechanical mode growth, embodied by Phoenix A, channels energy into kinetic disruption rather than radiation. The contrast between these two modes gives physicists a rare window into the growth limits of supermassive black holes. By comparing their efficiencies, fueling histories, and environmental dependencies, researchers can map out how black holes reach their extreme masses under different cosmic conditions. Modern simulations suggest these two giants are not anomalies, but prototypes, representatives of black hole behavior in the late universe, where gas becomes scarce and clusters dominate gravitational landscapes. AI-driven predictive models point toward a future in which radiative giants like Ton 618 become increasingly rare, while mechanical titans like Phoenix A shape the thermodynamics of galaxy clusters for trillions of years. Yet this divergence invites a deeper question. What happens if these two archetypes ever cross paths in the evolving cosmos? To stand before a black hole is to stand before a place where space-time stops behaving like the quiet, obedient fabric we experience on Earth. Instead, it becomes a sculpted geometry defined by Einstein's field equations, Schwarzschild, Kerr, and Reisner-Nordström metrics describe the three foundational families of black holes, each a different solution to the curvature of space-time around mass, spin, and charge. Schwarzschild space is the simplest form. A spherical well where geometry folds inward with symmetrical precision. Kerr geometry twists that symmetry by introducing spin which drags space-time around with it like a cosmic whirlpool. Reisner-Nordström adds electric charge which modifies the horizon structure and challenges our intuition about what lies beyond it. These are not just mathematical solutions. They are landscapes. One of the most unsettling features of these landscapes is frame dragging. In a rotating black hole, space-time itself is forced into rotation. It whirls like water descending into a drain, pulling everything, including light, into its spinning flow. Even the path you wish to take is no longer your own. The universe steers you. Deeper inside, another transformation occurs. The light cone, which normally defines the boundary between what can and cannot happen, begins to tilt and then flips. Future and past lose their familiar alignment. Every possible future points inward, and the idea of choice evaporates. At this stage, the traveler is no longer moving toward a black hole. They are moving into a rewritten version of causality. The forces acting there stretch matter into shapes no material is built to survive. These tidal forces become so extreme that atoms themselves are pulled into elongated strands, a process that scientists grimly call spaghetti formation. Yet even before reaching such depths, the edges of the event horizon already shimmer with quantum unrest. Virtual particles flicker in and out of existence. Vacuum fluctuations ripple along the boundary, hinting at the unresolved conflict between general relativity and quantum field theory. Here in this region of warping trajectories and distorted time, the laws of physics begin to argue with themselves. And when they do, one truth becomes clear. In this place, time is no longer your friend. The event horizon is often described as a point of no return. But that phrase barely scratches the surface of what it represents. In the mathematics of black holes, the horizon is not a wall or a surface in the ordinary sense. It is a geometric boundary woven into the curvature of space-time, defined by the moment when outward pointing light rays can no longer escape to infinity. Its area is not arbitrary. It scales directly with the entropy of the black hole. A profound insight revealed by Bekenstein and Hawking, which suggests that the horizon encodes information like a cosmic ledger written onto space-time itself. When a black hole spins close to the Kerr limit, the horizon is dragged into an oblate shape, flattened along the axis of rotation. This distortion is not cosmetic. It reflects the tension between angular momentum and gravity. A tension so extreme that it reshapes the very geometry of the hole. Light attempting to escape from near this boundary undergoes an endless stretching. Gravitational redshift steals its energy and slows its climb until its wavelength grows so long that escape becomes meaningless. From a distance, the light fades into darkness long before it disappears. Near the horizon, time behaves with even less mercy. A clock carried by an observer, falling inward, ticks with perfect normalcy for them, yet appears to freeze from the perspective of a distant viewer. 1 minute near the horizon can correspond to years or centuries outside. This time, dilation is not an illusion. It is the structure of space-time reordering the flow of causality itself. Classical physics treats the horizon as a silent border, but quantum theory refuses to give it such peace. Vacuum fluctuations dance along its edge. Virtual particles separate and recombine. Temperature and entropy emerge from its geometry. All of it hints that the horizon is not an ending, but a threshold. And the question that lingers, heavy as gravity itself, is simple. What lies beyond that curtain? The accretion disk surrounding a black hole is the closest thing the universe has to a natural fusion reactor. Though fusion is only the beginning of what unfolds there. As gas spirals inward, it is crushed by gravity and whipped into a plasma so hot that temperatures reach billions of Kelvin. At such extremes, atoms lose all structure. Nuclei and electrons drift as free particles in a storm of radiation where the ordinary rules of chemistry no longer apply. Magnetic fields tangled in the turbulence of the disk twist, or snap, and reconnect in violent cascades. Each reconnection event unleashes flares more energetic than any explosion humanity could ever create. Bursts capable of outshining entire galaxies for brief moments. These eruptions reveal the dynamic heart of the disk, but the light they emit carries deeper secrets. Among the most important is the iron K alpha line, a spectral fingerprint broadened and skewed by relativistic effects. By studying its distortions, astrophysicists can measure the spin of the black hole itself, reading the warped geometry like an imprint left on the iron atoms racing near the speed of light. Beneath this radiance lies a complex machinery of viscosity and instability. The Shakura-Sonyaev model describes how microscopic turbulence transports angular momentum outward, allowing matter to drift inward. Yet modern studies show that this turbulence often arises from the magnetorotational instability, a subtle dance between rotation and magnetic fields that tears the disk into swirling eddies. The efficiency of this machine borders on the unbelievable. A maximally spinning Kerr black hole can convert roughly 42% of the infalling mass into pure energy. Nothing humans have ever built comes close. Every watt of power generated near the event horizon is proof that gravity can outshine any star when given the right conditions. And still, the accretion disk holds mysteries deeper than its heat and its violence, for this natural reactor produces something even stranger. Relativistic jets are among the most astonishing structures in the universe. Not because they are bright or massive, but because they should not exist as cleanly as they do. They emerge from the regions around rotating black holes, where magnetic fields thread through the ergosphere and become twisted by the violent drag of space-time itself. As the black hole spins, it drags these magnetic field lines into coils of unimaginable tension. The energy stored in those coils becomes so immense that plasma is hurled outward along the poles, forming narrow jets that accelerate to velocities approaching the speed of light. Near these speeds, even the rules of perception begin to warp. Light emitted from the approaching jet becomes Doppler boosted, appearing brighter and more powerful simply because the jet is racing toward the observer almost as fast as its own photons. From this boosting, astronomers can infer the jet's orientation and use subtle variations in brightness to measure the spin of the black hole driving it. What makes these jets extraordinary is not just their speed, but their scale. Some stretch for millions of light years, punching through intergalactic space like luminous spears. They sculpt galaxies by heating gas, suppressing star formation, and carving cavities through the cosmic medium. Entire galactic ecosystems can be rearranged by a single sustained jet eruption. Among the most powerful known are the mechanical jets of Phoenix A. These colossal outflows have carved out cavities so vast that they dwarf entire galaxies, leaving behind structures that record the history of eruptions spanning tens of millions of years. The presence of such jets shows that black holes are not passive consumers. They are cosmic sculptors. They shape the universe as much as gravity shapes them, and the deeper we study these beams of relativistic light, the clearer one truth becomes. A black hole does not merely swallow. It carves its story into the cosmos. The growth of a black hole is not a single process, but a cosmic biography. A sequence of stages that begins with seeds far smaller than the titans they eventually become. In the early universe, when the first stars ignited and the cosmic fog began to lift, some regions collapsed, not into stars, but directly into black holes. These direct collapsed black holes formed from dense, pristine gas clouds that never fragmented, creating seeds thousands or even hundreds of thousands of solar masses. They were rare but powerful starting points. The ancestors of the supermassive black holes we witness today. Once a seed forms, its growth is dictated by hunger. Under normal conditions, the Eddington limit sets a cap on how quickly matter can fall inward before radiation pressure pushes back. Yet, the universe often ignores its own speed limits. Inflows can become dense enough to trigger super Eddington accretion, allowing the black hole to grow far faster than classical physics predicts. Gas funnels inward with such ferocity that radiation becomes trapped, unable to escape before being swallowed. This makes the process astonishingly efficient and accelerates growth during short cosmic windows. But feeding alone is not enough to create giants like TON 618 or Phoenix A. Mergers between black holes provide the next great leap. When galaxies collide, their central black holes spiral together, releasing gravitational waves that ripple across space-time. The final coalescence adds their masses and their spins, creating a new black hole whose properties reflect the violent history of its parents. In the dense environment of galaxy clusters, growth can escalate further. Runaway accretion occurs when inflows and feedback reinforce each other. Hot gas cools and flows inward, feeding the core, while jets and shock fronts reshape the surrounding medium to funnel even more material back in. This forms a feedback cycle with phases of voracious feeding, explosive outbursts, quiescent recovery, and renewed accretion. A rhythm of cosmic breathing that drives black holes toward extreme scales. The universe did not sculpt giants randomly. It followed this wheel of evolution, a wheel that forged the unimaginable masses of TON 618 and Phoenix A. Hawking radiation is one of the strangest predictions in physics because it tells us that a black hole, the very symbol of inescapable gravity, can slowly vanish into nothing. The process begins with the quantum foam that seethes along the event horizon. In this chaotic vacuum, pairs of particles and antiparticles continuously form and annihilate. Most of the time, the pair disappears before anything meaningful occurs. But near a horizon, the geometry of space-time interferes. One particle can fall inward while its partner escapes. To an outside observer, the escaped particle appears as radiation emitted by the black hole itself. The cost of that emission is paid in mass. Over unimaginable spans of time, a black hole loses energy and gradually evaporates. Even a supermassive black hole would require more than 10 to the power of 60 years to disappear. A duration so vast it dwarfs the age of the present universe. Yet, however faint this radiation may be, it carries thermodynamic information. It has a temperature, an entropy, a spectrum shaped by the geometry of the horizon, suggesting that the horizon is not truly silent, but behaves like a surface with microscopic degrees of freedom. These hints whisper of a hidden structure that classical general relativity does not describe. And whispering even louder is the connection between Hawking radiation and the information paradox. If radiation leaks away and the black hole eventually vanishes, then what becomes of the information carried by everything that ever fell in? Does the universe allow information to be destroyed, or does it encode it somewhere beyond our understanding? This is the question that lingers like an unanswered echo. Where does the information go? The black hole information paradox is one of the deepest wounds in theoretical physics, because it forces two pillars of modern science to disagree about how the universe works. Quantum mechanics insists that information can never be destroyed. General relativity insists that whatever crosses an event horizon is lost to the outside world. The conflict becomes unavoidable when we imagine matter falling into a black hole. If matter carries information, as every quantum state does, then where does that information go once the black hole swallows it? Hawking's original calculation offered a bleak answer. According to the mathematics of Hawking radiation, the radiation that escapes carries no imprint of what fell in. If a black hole evaporates entirely, the information appears to vanish with it. This outcome violates the unitary evolution of quantum mechanics and would fracture the foundations of physics. Leonard Susskind and others fought this conclusion by proposing the holographic principle. The idea that all information absorbed by a black hole is not destroyed, but encoded on its horizon in a lower dimensional form. In this view, the horizon becomes a cosmic storage device, and the universe behaves like a hologram, where the full three-dimensional information is written on a two-dimensional boundary. Yet this elegant idea meets a new challenge. The firewall paradox suggests that if information is preserved, then the region just inside the horizon must be filled with high-energy quanta, creating a searing wall of fire that contradicts the smooth geometry predicted by general relativity. One of these principles must give way. The paradox is a sign that our descriptions of space-time and quantum fields cannot both be complete. Emerging research hints that the true resolution may lie in the topology of quantum space-time itself, where geometry fluctuates and information threads through microscopic bridges invisible to classical physics. In such a framework, information is never lost. It simply takes paths we do not yet know how to follow. And if this is correct, then the truth waiting at the heart of every black hole could rewrite our understanding of the universe. Wormholes occupy a peculiar place in physics because they sit exactly at the border between what the universe forbids and what mathematics still allows. The idea began with the Einstein-Rosen bridge, a classical solution to general relativity that connects two regions of space-time through a folded geometric throat. In the equations, this bridge is entirely real. Yet it collapses too quickly for anything to cross. It is a door that opens for an instant and then vanishes before one can take a single step. The dream of a traversable wormhole requires something stranger. To hold such a tunnel open, space-time must be threaded with matter that possesses negative energy density, a form of exotic material that violates the usual energy conditions of relativity. Quantum field theory suggests negative energy can exist briefly through phenomena such as the Casimir effect. But sustaining it on macroscopic scales remains beyond anything observed. Even so, quantum back reaction offers a glimmer of possibility. Fluctuations in the quantum vacuum can, in principle, modify the throat of a wormhole, stabilizing it for moments longer than classical relativity predicts. These would not be portals for travel, but fleeting passages where geometry folds in ways unfamiliar to ordinary intuition. Some simulations show that in certain black hole binaries, the extreme curvature and dynamic horizons can produce transient structures that mathematically resemble wormholes. They are not traversable and vanish almost instantly. Yet they remind us that space-time is capable of architectures far stranger than we once believed. No telescope has ever seen a wormhole. No detector has ever found the signature of one, and yet there is nothing in the mathematics of the universe that forbids their existence. They wait in the space between theory and imagination, suspended like unanswered questions carved into geometry. And it leaves us to wonder what might be possible if a titan like Ton 618 possessed the right conditions to act as a cosmic key. A merger between two supermassive black holes is not simply an astronomical event. It is a restructuring of space-time on a scale so overwhelming that even the universe seems to pause and take notice. When two titans spiral toward each other, their accretion disks do not glide together peacefully. They are torn apart by tidal forces strong enough to unbind entire galactic structures. Streams of plasma stretch into luminous arcs. Magnetic fields snap and reform. Shock waves ripple outwards through interstellar gas like the echo of a cosmic scream. And while matter is ripped apart, gravity begins its own dance. The inspiral of two massive horizons produces gravitational waves of a magnitude far beyond anything detected by LIGO. Those waves would not hum. They would roar, reshaping space-time with a violence that could be felt across clusters of galaxies. At the moment of coalescence, the newly formed black hole receives a recoil kick, a burst of momentum created by asymmetric emission of gravitational waves. In extreme cases, that recoil can be powerful enough to eject the merged black hole entirely, flinging it out of its host galaxy like a stone hurled from a sling. The timescale of this titanic encounter is equally vast. From the first measurable perturbations to the final union, the process can span hundreds of millions of years, a slow cosmic choreography guided by gravity's relentless pull. Yet, when the final moment arrives, it comes with a brilliance unprecedented in cosmic history. For a brief instant, the energy released rivals the combined luminosity of trillions of stars. The universe records the event not in light, but in the curvature of space-time itself. And all of this describes an ordinary merger between giants. What then would unfold if the colliding monsters were Ton 618 and Phoenix A? Comparing Ton 618 and Phoenix A is not a contest of size or brightness. It is a study of two radically different ways a black hole can dominate the universe. Ton 618 represents the radiative extreme. A quasar so luminous that its accretion disk pours out electromagnetic light with the fury of 1 trillion suns. Almost all its power escapes as radiation. The disk becomes a furnace of relativistic plasma, and the black hole's rapid spin channels this energy outward with astonishing efficiency. A Kerr black hole spinning near its maximal value can convert a remarkable fraction of infalling mass into light. And Ton 618 appears to dance close to that limit. Its brilliance is not an accident. It is the signature of a black hole that has mastered the radiative mode of growth. Phoenix A stands on the opposite end of the spectrum. It is the mechanical titan whose true strength emerges not from light, but from force. Fed by an enormous cooling flow in the Phoenix cluster, it channels its energy into jets, shock fronts, and the excavation of cavities larger than entire galaxies. Its luminosity is modest compared to Ton 618 because most of its energy does not become light. It becomes momentum. It becomes pressure. It becomes the rearrangement of an entire cluster's thermodynamic structure. In many mass models, Phoenix A surpasses TON 618 outright, reaching an upper bound near 100 billion solar masses. TON 618 may outshine it, but Phoenix A outweighs it. Spin adds another twist to the comparison. TON 618 likely spins faster, which gives it a higher conversion efficiency and makes its quasar mode extraordinarily radiant. Phoenix A may spin more slowly, but its environment provides so much fuel that radiative efficiency becomes irrelevant. The real contest between them would not be their appearance, but their merger. If these titans ever spiral together, the radius of the final event horizon would exceed 1 light-year. This single object would warp space-time on a scale comparable to an entire small galaxy. Two archetypes of cosmic evolution meeting in a collision beyond imagination. Yet the last question hovers in the silence between them. Does the universe permit two such titans to ever meet? The distant future of the universe is not a place of stars. It is a landscape sculpted almost entirely by black holes. As the cosmos ages, the great engines of starlight burn out one by one. Massive stars collapse into neutron stars or black holes. Smaller stars fade into white dwarfs and eventually cool into darkness. With each passing epoch, the luminous population thins and the gravitational skeleton becomes more pronounced. Black holes begin to dominate the architecture of everything that remains. Galaxies collide and merge in an ancient ritual known as galactic cannibalism. Their central black holes spiral together through oceans of dark matter and gas, merging again and again in a cosmic lineage of ever-growing gravitational titans. What emerges is a universe where black holes are not rare monsters, but the primary nodes of structure, the anchors around which everything else orbits or falls. As time stretches into the dark era, baryonic matter becomes sparse. The fusion furnaces of stars no longer replenish the balance of energy. Gas clouds disperse. Planetary systems drift apart. What survives these epochs are black holes drifting through the deepening cosmic night. In such a future, AI-driven cosmological models predict a striking transition. Over timescales of 10 to the power of 15 years, the number of black holes will surpass the number of stars. The cosmos becomes a cemetery of collapsed matter. Each black hole carrying the frozen history of whatever once fed it. The event horizon itself becomes a measure of age. As black holes slowly evaporate through Hawking radiation, their shrinking horizons tell a story of time far longer than any stellar clock could measure. They become the chronometers of a dying universe. Yet, even in this era, one truth remains. Black holes do not live forever. Their apparent permanence is an illusion, stretched across immense spans of time, but not truly eternal. And that realization leads to a deeper question lingering beneath the darkness. If even black holes fade, what then is left to inherit the universe? The death of a black hole is not a collapse, but an unraveling. It begins so slowly that no civilization could ever witness its early stages. Hawking evaporation works on a timescale that dwarfs every cosmic calendar we know. A stellar mass black hole requires around 10 to the power of 60 years to vanish. A supermassive one may endure for 10 to the power of 100. These spans are neither poetic nor metaphorical. They are longer than the lifetimes of galaxies. Longer than the rise and fall of all stars. Longer even than the memory of matter itself. And yet the process follows a simple rule. The smaller a black hole becomes, the faster it evaporates. As mass is lost, the temperature of the horizon climbs. Radiation intensifies. The horizon shrinks more rapidly. Eventually, a runaway phase begins and evaporation accelerates into something closer to a final fever. There are hints that at the end the black hole may not disappear entirely. Some quantum gravity models predict a Planck scale remnant. A relic so small and dense that space-time itself refuses to collapse further. Whether this remnant exists remains uncertain. But its possibility suggests that even in death, a black hole might leave behind a seed of the geometry that once defined it. For giants like TON 618, the end lies so far beyond imagination that the current universe is merely their childhood. Its evaporation time exceeds the age of the cosmos by more orders of magnitude than the human mind can comfortably hold. It will drift through the dark era as one of the last major structures in existence, shrinking imperceptibly as aeons pass. When the final moment arrives, the black hole releases a short, explosive burst of radiation. The last breath of a horizon that once commanded the lives of galaxies. Then the darkness that consumes so much finally consumes itself. But even in that ending, one question lingers. What does a dying black hole leave behind for the universe to remember? When a black hole dies, it does not vanish without consequence. The universe keeps a memory of every titan that ever existed. Long after the event horizon shrinks into nothing, the gravitational imprint it once carved into space-time persists like a faint scar. Regions that once orbited the black hole continue moving along distorted trajectories, guided by a curvature that no longer has a source. Geometry remembers even when matter forgets. On much larger scales, galaxies preserve fossil signatures of ancient quasars. The halos surrounding them carry thermal relics left by jets that blasted through intergalactic space millions of years ago. Cavities remain carved into the gas. Shock fronts linger as silent ripples. Even when the quasar itself extinguishes, these fossil structures become the only surviving testimony of a past era of brilliance. Space-time itself also records the lives of black holes. The final merger of two giants sends gravitational waves across the universe. And those waves do more than pass through matter. They modify the metric permanently in tiny but real ways. This phenomenon, called gravitational wave memory, functions like a cosmic fossil. An imprint frozen into the fabric of the cosmos long after the waves themselves have faded. It is possible that in the far future, when no stars remain and even black holes have evaporated, the universe will still carry these subtle distortions. They will form the archaeological remnants of a cosmos that once teemed with light and fury. Such fossils could become the only clues available to any future intelligence attempting to reconstruct the universe's vanished giants. They would study faint metric echoes, residual curvature, thermal scars, and spectral anomalies embedded in the cosmic background. A map of ghosts written not in matter, but in geometry. And beyond these relics lies a stranger possibility still lingering just outside the borders of known physics. The idea that black holes might act as engines of dark energy lies at the edge of current physics, a domain where speculation meets mathematics and the universe quietly hints at deeper rules. Some theoretical models propose that the cores of certain black holes do not collapse into a singularity, but transition into a de Sitter region, a bubble of space-time driven by positive vacuum energy. In such models, the interior behaves less like a point of infinite density and more like a pocket of accelerated expansion contained behind the horizon. From the outside, nothing seems unusual. Yet, deep within the geometry, a second horizon forms. A hidden membrane that reshapes the way energy and information circulate. Extreme spin may amplify this effect. A maximally rotating Kerr black hole stores vast amounts of extractable rotational energy. The interplay between spin, vacuum polarization, and quantum back reaction could in principle generate conditions similar to those associated with cosmic acceleration. If such internal dynamics aggregate across billions of galaxies, the cumulative effect might influence the expansion rate of the universe. Some AI-driven cosmological analyses even predict that ultramassive black holes could subtly modify the large-scale structure by acting as regulators of vacuum energy. They would not control the cosmos, but they might tune it, functioning as pressure valves that stabilize expansion over long epochs. This view reframes black holes not merely as destructive endpoints of matter, but as active participants in the cosmic feedback loop. They swallow mass, store rotational energy, alter curvature, and potentially contribute to the overall balance of dark energy. Such ideas remain unproven, but they represent a growing frontier in theoretical astrophysics. They ask whether the universe's engines of destruction might also be its architects. What if black holes do not only break the universe apart? What if they help build it? Black holes may be the strangest libraries in the universe because they do not archive their stories in pages or symbols, but in geometry. According to the holographic principle, the event horizon acts as a two-dimensional surface that encodes all the information about the three-dimensional world that falls into it. Entropy becomes the measure of this storage capacity, and for a Titan-sized black hole, the number is staggering. A single ultramassive horizon can hold more than 10 to the power of 90 bits of information, far exceeding the storage capacity of any structure known to physics. These bits are not arranged as text, but as microscopic configurations of space-time itself, a pattern written into curvature. Yet the universe provides another, subtler archive. The photons released from an accretion disk carry the fingerprints of everything that unfolded near the horizon. Their spectra encode the violence of infall, the geometry of rotation, magnetic turbulence, relativistic shear, and even the evolutionary history of the surrounding galaxy. Long after the disk has faded, these photon patterns become fossils of cosmic memory. They preserve the thermodynamic story of how matter died and how light survived. Some AI-driven theoretical frameworks take this one step further, proposing that black holes function as compression engines that store the universe's memories in their holographic layers. Instead of destroying history, they condense it, transforming events into geometric data that remains as long as the horizon exists. TON 618 is one example of such a cosmic vault. The light that blazes from its quasar is built from the shredded remains of millions of stars. Their final signatures survive in the turbulence of its disk and in the curvature of its horizon. What we see as pure radiance is in fact a transcription of stellar deaths, written in the language of gravity. And if black holes are libraries, then a final question quietly arises. Which book are we reading when we look into one? White holes exist first as equations long before they exist as objects. They emerge from the time-reverse solutions to Einstein's field equations. mathematical siblings of black holes that behave like mirrors turned inside out. If a black hole is a region where nothing can escape, a white hole is the opposite. A region where nothing can enter. Matter can only emerge from it, streaming outward as though pushed by an invisible boundary. In the classical view, this symmetry is elegant but useless. The universe does not appear to allow such objects to form. No known astrophysical process generates them, and any incoming disturbance would destabilize them instantly. They seem to belong to mathematics rather than nature. Yet quantum gravity complicates this picture. Some theories propose that when a black hole reaches the final Planck scale of its evaporation, space-time may undergo a quantum bounce. Instead of collapsing into a singularity, the geometry could rebound, transforming a dying black hole into a transient white hole. Its interior would no longer swallow information but expel what had been compressed, releasing it in a final burst that mirrors the earliest conditions of the universe. More ambitious cosmological models extend this idea far beyond individual objects. They suggest that the entire universe may have originated from a white hole-like event, an expansion emerging from a collapsed precursor in a previous cosmic cycle. In this interpretation, the Big Bang is not a beginning, but a transition. A moment when geometry flips from inward collapse to outward surge. Whether any of this is realized in nature remains unknown. No telescope has ever detected a white hole, and no gravitational wave has carried its signature. But the mathematics refuses to dismiss them, and quantum theories continue to resurrect their possibility. If white holes are real, they would force us to rethink not only the life cycle of black holes, but the life cycle of the universe itself. And that leads to a question that grows harder to ignore. If TON 618 will one day finish its long evaporation, what will it become? Imagining the final century of TON 618 is like imagining the last whisper of a dying universe. By the time this titan reaches the far future of 10 to the power of 100 years, every star will have faded, every galaxy will have dissolved, and space-time itself will have stretched into a cold and nearly featureless void. In this silence, TON 618 continues its slow unraveling. Its event horizon shrinks at a pace so small that even cosmic time seems impatient. Hawking radiation trickles outward in particles so low in energy that they barely disturb the darkness around them. The once roaring quasar has long been extinguished. There is no accretion left to feed it. No mergers remain to enlarge it. The cosmic web has thinned to the point where TON 618 drifts through an ocean of almost perfect emptiness. What remains is only the black hole and the quantum processes gnawing at its mass. As it contracts, its temperature rises. A black hole that once contained billions of suns becomes a quantum ember glowing with increasing intensity. The geometry inside grows more unstable. The final phases approach as the horizon reaches microscopic scales. Whether it collapses into a Planck-sized relic or undergoes a quantum bounce is a question no current physics can answer. Yet all models agree on one thing. There is a last moment. A final burst. When the temperature soars to unimaginable levels, the black hole releases its remaining energy in a single, brilliant explosion. It is not a supernova, but a farewell of space-time itself, a fragment of the cosmos returning to the vacuum that birthed it. In that instant, the long night of the universe is illuminated by what is essentially the last firework of the Dark Era. Ton 618's final breath. But the question that lingers is larger than the event. Will anyone or anything still exist to witness it? In the long contest between life and gravity, the question becomes unavoidable. Which will endure longer? Civilizations or black holes? A sufficiently advanced species 1 approaching Type 3 on the Kardashev scale would not fear a black hole. It would treat it as the ultimate power source. Unlike stars which fade, black holes grow hotter as they shrink, radiating more intensely as Hawking evaporation accelerates. Far in the future, a civilization that understands these mechanics could build structures not around stars, but around horizons. A Dyson sphere encircling a black hole would be smaller, denser, and far more efficient than one built around a star. In theoretical classifications, such a society would rank beyond Type 3, earning a place sometimes called Kardashev 3, 5. At this level, the civilization no longer depends on stellar fusion. It draws energy directly from space-time itself. The Blandford's-Narjek mechanism would become its master tool. By tapping the rotational energy of a spinning black hole through magnetic fields, the species could extract power equivalent to that of entire galaxies. To them, the black hole becomes a controlled engine, a gravitational turbine, spinning out usable energy for as long as its spin can be maintained. AI-driven projections suggest an inevitable pattern. Any species that survives long enough to reach cosmic maturity will choose black holes as their final suns. Stars die. Matter thins. But a black hole, especially one with moderate mass, can power technology for trillions of years. In such an epoch, life could outlast galaxies, dwell beside horizons, and build its continuity on the endurance of gravity. Yet, such a future raises a quieter question. We imagine surviving beside these engines of darkness, but are we ready to speak with them? Are we prepared for a dialogue with the very objects that will one day outlive the stars? Black holes are silent in theory, but noisy in practice. Across the last decade, our most advanced observatories have recorded signals so peculiar that they strain the limits of current physics. TESS, a mission designed to search for exoplanets. Unexpectedly detected quasi-periodic eruptions around certain black holes. These eruptions occur with astonishing regularity. As though a compact body or a warped region of space-time is orbiting just outside the edge of stability and sending out pulses every time it completes a loop. Their periodicity is too clean to be random, yet too unstable to match classical accretion models. Meanwhile, the Chandra X-ray Observatory has captured flares that brighten and fade in repeating cycles. Some occur on timescales of minutes, others on hours, all suggesting that magnetic fields near the event horizon are reconnecting in patterns more structured than turbulence should allow. These X-ray flashes reveal a choreography of plasma that seems to know its own rhythm. Hubble has contributed its own puzzle pieces by observing jets whose twisting motions do not match the predictions of simple Kerr geometry. Instead, the jets wobble in ways that imply precession. Frame dragging gradients, or even disturbances from unseen companions. Some of these jets shift faster than expected, as though the underlying space-time is vibrating. And then there is JWST, Its deep field surveys have revealed quasars that appear fully formed at epochs when the universe was barely a few 100 million years old. According to our models, black holes that massive should not exist that soon. Either they grew far faster than GR-based accretion allows, or they formed from seeds unlike anything we have ever imagined. Across all these observations, a pattern emerges. None of them quite fit within the clean borders of general relativity. They require extra ingredients, new physics, or deeper interpretations of space-time itself. And when data begins to misbehave in consistent ways, it raises a provocative question. Is the universe trying to send us a signal? For all our equations and simulations, black holes remain the most misunderstood architecture in the universe. Every discovery draws a sharper outline, yet the core remains untouched. The first mystery is the singularity. In classical general relativity, it is a point of infinite density, but infinity is a confession of ignorance, not a solution. Whether the singularity is a geometric defect or a quantum region with an entirely new topology is still beyond our reach. The second gap lies at the event horizon, where space-time slopes into a regime so steep that Planck scale effects should dominate. Our current models do not have the mathematical language to describe what the horizon becomes when quantum geometry takes over. Another unanswered question concerns the relationship between black hole growth and dark matter halos. Galaxies with heavier halos tend to host more massive black holes, yet the causal chain is still invisible. Does dark matter seed early collapse, or does the black hole sculpt the halo? We do not know. The tension grows when we look backward in time. JWST has revealed supermassive black holes existing far earlier than theory allows. They appear fully formed when the universe should not have had enough time to build them. This single fact threatens to rewrite the story of structure formation. And still the puzzle deepens with the jets. These beams extend for millions of light years, yet their stability implies a magnetic architecture far grander than anything inside the accretion disk. How black holes braid, collimate and preserve such fields across cosmic distances is one of astrophysics' unsolved riddles. Each of these mysteries casts a long shadow across our understanding. We see the silhouette clearly. What we have not yet seen is the hand that throws that shadow. Black hole physics has reached a point where observation advances faster than interpretation. The biggest controversies in the field are not arguments over details, but arguments over the foundations of reality itself. The first and most famous debate concerns the no-hair theorem, which claims that a black hole is fully defined by its mass, spin, and charge. Yet quantum models increasingly suggest the existence of quantum hair, subtle imprints of information that cling to the horizon. If quantum hair exists, the horizon is not a featureless surface, but a dynamic ledger of everything that has ever fallen in. The second controversy circles the information paradox. If information is truly lost, then quantum mechanics is incomplete. If it is preserved, then general relativity cannot be the full story. Either way, one of physics' pillars must bend. The third unresolved question is the true shape of the singularity. GR insists on a point of infinite density, but that point violates every principle of quantum field theory. Some researchers envision a ring singularity. Others imagine a finite core structured by quantum geometry. None of these models are yet provable. The fourth debate asks whether a black hole could bounce. Instead of ending in evaporation, the interior might undergo a quantum conversion, transitioning into a white hole. A new universe, or a metastable pocket of space-time. Such models challenge the very notion of a one-way collapse. Finally, there is a radical idea that a black hole might not be a macroscopic object at all, but an exotic particle, an ultra-massive quantum excitation whose gravitational field mimics a classical horizon. If true, the boundary between particle physics and astrophysics dissolves entirely. These controversies mark the frontier of modern physics. Here, observation is ahead of theory, and theory is ahead of understanding. The field stands before what feels like its final war. When artificial intelligence is allowed to extrapolate the laws of physics across timescales far beyond human intuition, it paints a universe that dissolves gently into its own mathematics. In the deep future, galaxies no longer behave as coherent structures. Their stars drift apart under the pull of dark energy, leaving only compact remnants to sink toward the gravitational centers that still exist. Over unimaginable epochs, black holes begin to dominate the inventory of matter. They migrate, merge, and reshape the cosmic landscape until clusters collapse into hierarchies of gravity. In these mergers, AI predicts the emergence of titans, colossal black holes that dwarf even TON 618 and Phoenix A. Each merger increases mass, reduces spin, and imprints the fabric of space-time, with gravitational memories that ripple long after the event. As the universe continues to expand, the isolated titans become the last anchors of structure. They mark the final architecture of the late cosmos, vast regions of darkness punctuated by a few gravitational giants. Eventually, even these giants succumb to Hawking evaporation. Their horizons contract, releasing faint radiation across timescales of 10 to the power of 100 or more. What remains after the final black hole evaporates is not emptiness, but a quantum fog. In this regime, space-time loses its smoothness. Distances fluctuate, time wavers, and the Planck scale becomes the only meaningful yardstick. The universe becomes a sea of probabilistic tremors, a field of pure quantum granularity, without stars or atoms or horizons. In this limit, even the concept of shape dissolves. The cosmos does not end. It becomes undefined. And yet, before that far horizon of meaning fades, there is one question that humanity cannot escape. When the universe enters its long twilight and gravity becomes the final sculptor of structure, only a few titans remain to anchor the fading cosmos. The natural question follows. Between TON 618 and Phoenix A, which one becomes the last to stand? The physics suggests that Phoenix A has an advantage written into its environment. Nestled inside a dense galaxy cluster, it feeds on an almost inexhaustible reservoir of intracluster gas. Cooling flows continually deliver fresh material, allowing the black hole to grow even when the rest of the universe becomes starved of fuel. Its growth mode is mechanical rather than radiative, which means feedback does not shut itself down. It can continue consuming, sculpting, and expanding over cosmological timescales. TON 618 follows a different path. Its radiative mode burns bright, but limits its own appetite. As the accretion disk intensifies, radiation pressure rises and prevents further inflow. The brilliance that defines TON 618 is also the mechanism that restrains it. Yet TON 618 holds an extraordinary advantage. Its spin is extreme. A rapidly spinning Kerr black hole extracts energy with unmatched efficiency, turning infalling matter into luminous output far beyond the mechanical power of Phoenix A. Its accretion episodes are shorter but more explosive, rewriting the structure around it with every surge. AI-driven cosmological projections show a pattern emerging. Phoenix A grows steadily, while TON 618 burns violently. Over trillions of years, the stable feeder outlives the flare. Phoenix A is more likely to remain active deep into the dark era sustained by cluster-scale fueling, while TON 618 fades once its surrounding environment is exhausted. But this was never a contest of strength. It is a prophecy written in gravity's own language. The deeper we study the cosmos, the clearer a quiet verdict emerges. Black holes are not exotic exceptions. They are the fate toward which all structure slowly drifts. As dark energy stretches the universe and galactic bonds loosen, every star system becomes vulnerable to dispersal or collapse. Over vast epochs, entire galaxies thin into ghost-like scaffolds. What remains dense enough to survive the long unraveling ultimately slides into the gravity wells waiting at cosmic centers. In this sense, every structure, no matter how luminous, is already walking a path that ends in a black hole. Black holes are not merely endpoints. They are the gravitational crossroads of the universe, the inevitable sum of every interaction shaped by mass, motion, and time. Remove black holes from the cosmic script, and the universe as we know it collapses conceptually. Without their anchoring pull, galaxies could not form. Without their feedback cycles, the balance of star birth and star death would fail. Without their presence, the large-scale structure of the cosmos would lack hierarchy, coherence, and rhythm. They destroy, but they also define. They erase, but they also carve. They consume, yet they also create the environment in which galaxies can breathe. This duality makes them both executioners and architects. The universe's past is written in their accretion scars, and the universe's future is molded by their mergers. In the far future, when matter thins and stars fade, the destiny of the cosmos becomes indistinguishable from the destiny of its black holes. The final architecture of everything is ultimately their architecture. And that future, whether shaped by titans like TON 618 and Phoenix A, or by the countless remnants that come after, is already whispering our name. In the end, the universe does not raise its voice. It does not warn or argue or plead. It reveals. Slowly, patiently, one monster at a time. Black holes were never meant to be mysteries. They are declarations written into the fabric of space-time, reminders of how far human understanding can reach before it fractures. TON 618 and Phoenix A are not outliers. They are the opening chapters of a book humanity has been afraid to open because every page demands that we rewrite what we thought we knew. To study a black hole is to stand at the boundary between the known and the unknowable. Every horizon whispers that the laws we trust are temporary, that our equations are sketches rather than truths, and that the universe is a manuscript still being edited by forces older than light. When we look into a black hole, we are not observing the fate of distant galaxies. We are looking at a reflection of our own future. A future where our curiosity is tested, our imagination is stretched, and our humility is demanded. Because the cosmos does not reveal itself to those who fear the dark. It reveals itself to those who walk toward it. Stay curious. Stay critical. And before the last light fades, Ask yourself one final question. Are you ready to look into the place where even light gives up?